Hi guys, welcome to a new video. In this opportunity guys, we want to calculate the electric field that is produced by a ring of charge. So we have some considerations at the very beginning, and those considerations are the following. First, we have a ring that is charge is Q. The charge Q is uniformly distributed along the ring. So that means that the charge is constant. Second, that we have a density, right? Linear density of charge that is a constant. Also, I want to consider that the charge is positive. So the charge is positive. Okay, is greater than 0, and we have a positive charge on this ring. All right, we want to calculate the electric field at this point P. Okay, let's get into it. First, I want to write the density of the ring, because I said that the charge is constant. We will have a density that is constant. Also, I want to say that this problem is a problem in the superposition of electric fields. That means that we will superpose the electric fields of too many little pieces of charge to calculate the total field along the x-axis. All right, along the x-axis. Okay, the density of charge for the whole ring, to calculate the density of charge, I have the charge Q of the ring, okay, and I have the length of the ring. We remember the ring is a circumference, and its length by definition is 2p multiplying the radio. All right, the length is 2p multiplying the radio, and by definition the linear charge density for this ring is equal to lambda. We call the density lambda equal to charge dividing length, but we know that the length is 2pa. We call this equation number 1. Okay, we come back to the illustration and we see this little element on top of the ring. That little element has charge dq and length ds. All right, so by definition we said that the linear density is constant. That means that the whole ring has the same density as the little piece as well. So the little infinitesimal segment has the same linear density of charge as the whole ring. So the charge of the segment is dq, its length is ds, then its density is equal to lambda dq dividing ds. I call this equation number 2. All right, so what I'm gonna do is this. Because the lambda is constant, we can make equations 1 and 2 equal. We can make equation 1 equal to equation 2. Then I will have that dq dividing ds is equal to q dividing 2pa. All right. Now I will take this ds in the denominator. I will send it to the other side of the equation to multiply. And finally, I will have dq is equal to q dividing 2pa multiplying ds. I will call this equation equation number 3. I will hold on this equation. All right. Let's highlight it. We will use it later. Okay, guys? Well, now we consider two identical segments in the illustration. So let's go back to the illustration. I will consider two identical segments, one on top of the ring and one on the bottom of the ring. The distance between the center of the circumference and the element on top is the radius a, and we call the distance y equal a. But the distance between the center of the circumference and the element on the bottom of the ring is minus a. All right. So this element on the bottom has charge dq and length ds as the element on top. So they are identical. They have the same charge and they have the same length, but they produce an electric field on the point P, at the point P. So those two elements are symmetrical, right? They are equal, but they are opposite for the symmetry of the problem. So if we analyze the electric field that is produced by the element on top, this is the electric field. This is the electric field. I will use blue color. This is the electric field that is produced by this element. Okay? This is the electric field, and the electric field is pointing away from the element because the charge is positive. Okay? That's something that happens when the charge is positive. The electric field points away from the charge or from the element of charge. This electric field that is illustrated by the blue arrow has two components: the component along the x-axis and the component along the y-axis. Okay, now I go to the element on the bottom. This element is producing an electric field at the same point P, but the field is pointing to this direction. Okay, that electric field has two components as the first element as well. The S component is pointing to the same direction. Okay, but the Y component, the vertical component, is pointing upwards. So, and this direction is opposite to this one. So these two components, the vertical components they cancel each other. Why? Because they are equal and opposite. So, and the same happens if I take an element here and an element here, that they are equal but opposite. If I take one element here and one element here, then they are equal and opposite. So for all the elements along the ring that are equal and opposite, the y component of the electric field is gonna be cancelled, because the components of the two elements that are equal and opposite cancel each other as well. So I hope this explanation is clear for you guys. What we have by the end of the problem: the total sum of for all the y components of each segment in the ring is going to be 0. Then we won't have electric field along the y-axis. The only component of the electric field that we will have remaining is the component along the x-axis. So because we will have that, the only component that we will have finally of the electric field is going to be E equal to Ex. Let's call this equation number 3.1, right? We know that y is the unitary vector, the unit vector along the x-axis, right? Unit vector along the x-axis. So the remaining component of the electric field is going to be finally the S component of the all distribution. All right. So let's come back to the algebra on this problem. Come back to the illustration and see. I will erase all this to have a more clear illustration. Okay, by definition, the electric field that is produced by a charge is going to be E equal to 1 dividing 4p epsilon 0, multiplying the charge, dividing the distance between the charge and the point where you are waiting to calculate the electric field. What is this? This is a constant, right? This term that is 1 dividing 4p epsilon 0. Epsilon 0 is called electric permittivity of the free space. Q is the charge. R is the distance between the point or the charge and the point where you are calculating the electric field. So this is the definition of the calculation of the electric field. So we use this definition for this point dq, calculating the electric field on this point P. Okay. Well, if we use this definition, the electric field that is produced by the element, the element dq, is going to be the E is equal to 1 dividing 4p epsilon 0 dq dividing r squared. Let's go back to the illustration. This is the electric field produced by this element. The distance between the element and the point P is r, and by the Pythagoras theorem, r is equal to the root square s squared plus a squared. So we have a triangle right here. This is the x side, this is the a side, and the hypotenuse is going to be root square of s squared plus a squared. Okay, so we are using the Pythagoras theorem right here in this problem. So we have that for definition of the Pythagoras theorem, r squared is going to be equal to s squared plus a squared. Then if we replace this into this, I will have dE equal to 1 dividing 4p epsilon 0 dq x squared plus a squared. I will call this equation number 4. Okay, equation number 4. I will use it later. Now let's go to the illustration again. We are calculating only dx, okay? But dx, if we see this triangle, dx is equal to the hypotenuse multiplying cosine of theta, right? By trigonometry. This is the adjacent side. This is the hypotenuse, and this is the angle. And by definition, we have that this side is equal to the hypotenuse multiplying cosine of alpha. Okay? So we have that dex is equal to dE cosine of alpha. Then we know that finally this is the component we want to calculate, because we only have the horizontal component for the final electric field, right? So the EX is going to be, I replace this into this, equation number 4 into this equation, and I will have 1 dividing 4p epsilon 0 okay. I remember that I come back before finishing this, I come back here and I know that the Q is equal to equation number 3. Okay, so I know that the Q is equal to Q dividing 2p A multiplying the S. Okay, and I know that if I go to the triangle right here, to this triangle, cosine of alpha is equal to R dividing X, right? Sorry, X dividing R, right? So by definition, right? So I come here and I know that cosine of alpha is X dividing R. I will replace all this 2 into this. Then I will have 1 dividing 4p epsilon 0 dq, but dq is q ds dividing 2pa. Okay, dividing 2pa. I know that I will have okay, let's do something. But let's write something first. Before doing that, I will write the formula as the Q as number 4. Let's come back to number 4, dividing 2s squared plus a squared. Okay, cosine of alpha. And after I do this, I don't want to confuse things. Now I will do this. Now I will replace the q into this and cosine of alpha into this. Now I will do it. So I will do dx, the ex is equal to 1 dividing 4p epsilon 0. Okay, now let's do it. Now let's do it. The q is q dividing 2pa ds, okay? And cosine of alpha is x dividing r, okay? Let's write down this equation again right here to be more clear. 1 dividing 4p epsilon 0 multiplying q dividing 2pa q ds dividing 2pa x dividing r. Okay, oh okay, I forgot to write down here x squared plus a squared. Okay, I have to write down that. All right, so s squared plus a squared. Okay, we know that r is equal to root square of x squared plus a squared. Okay, we know this. Okay, so we use that here. We know that r is equal to root square of a squared plus x squared. Okay, and then we can write the equation like this. The ex is equal to 1 dividing 4p epsilon 0. Okay, this q dividing 2pa is lambda. Remember, right? Lambda is equal to q dividing the length of the circumference. Okay, so I will write this equation like this. Lambda ds multiplying x dividing s squared plus a squared multiplying s squared plus a squared power 1/2. Then the ex is equal to 1 dividing 4p epsilon 0. I will distribute it like this. Lambda x ds all this is going to be x squared plus a squared 3/2. Okay, now we will find the electric field integrating the expression over the entire ring, over the whole ring. So we will do an integration. Okay, so the integrand has the same value for all points on the ring, so we can take out the expression and the integral is going to be something like this. Okay, guys. I will integrate from 0 to the length of the circumference, that is 2pa ds. Okay, guys. This integral is equal to 2pa. Okay, guys. Then I will have finally the electric field is going to be equal, the component x is going to be equal to 1, because this is equal to ex. Okay. Finally, we will have something like 1 dividing 4p epsilon 0 lambda x dividing x squared plus a squared 3/2 power multiplying 2pa. Okay, guys. This, if I reorganize the expression like this, okay, lambda 2pa x lambda 2pa x dividing x squared plus a squared 3/2 power. We know that this is the charge q, because we know that we know that lambda is q dividing the length. Then if I take this term and send it to the other side of the equation, it's going to be lambda 2pa equal to q. So I can write q on this part of the equation, okay, on this part of the equation. And finally, the electric field along the x-axis is going to be 1 dividing 4p epsilon 0 multiplying the charge, the distance x squared plus a squared 3/2. Okay, guys, this is the electric field of a ring with charge q at a distance x along the x-axis. So the electric field at a point P that is along the x-axis at a distance s from the origin of the center of the ring. Okay, guys, this is the final expression. Hopefully you like this video. You can share it with your friends, and if you want to follow my channel, I would appreciate it. See you in the next video. Bye.